You know, we live in a world that's just built on numbers. We see them everywhere. The specs on your phone, the results of a lab test, you name it. And we have this natural tendency to trust them, to see a number and think, okay, that's the truth. But what if I told you that every single measurement ever made, no matter how precise it looks, is really just a very, very good approximation?
Right, let's really dig into this question because it gets to the absolute heart of how science actually works. It turns out, science isn't about finding one single, perfect, correct answer. Nope, it's about figuring out just how confident we are in the answer we've got. So, to really get what I'm talking about, let's try to do something that sounds pretty straightforward. We've got a piece of material here, and we want to find its electrical resistivity. That's just a fancy term for how much it fights against an electric current. Seems easy, right? Just hook up a power supply, grab a meter, and you're done. Well, the real world is always a little bit messier than that. Okay, problem number one. Our tools aren't perfect. You know those clean diagrams you see in a physics textbook? They show an ideal voltage source that pumps out a perfectly steady voltage. But a real power supply, the one on your bench, has this thing called internal resistance. The best way to think about it is like a tiny hidden tax on its power. The second you try to use it, that resistance kicks in and the voltage drops a little. So the voltage your material is actually seeing is already different from what your power supply says.
Oh, and it gets worse. A lot worse. The wires you use to connect everything, even the tiny points where your probes make contact with the material, yep, they all have resistance too. So if you try to do a simple two-probe measurement, you're not just measuring your material. You're measuring the material plus the wires plus the contacts. Your reading is already corrupted from the start. So the big question becomes, how on earth do you measure only the thing you want to measure?
Well, to get around this, scientists came up with a truly clever, almost beautiful solution. It's called the four-point probe technique. And its genius comes down to one simple, brilliant idea. Separate the path the current flows through from the path you use to measure the voltage.
Here's how it works. First, you take two probes on the outside, and you push a specific amount of current through them. That current flows into the material and spreads out. Then, and this is the clever part, you use two completely separate probes on the inside to measure the voltage. Now, a good voltmeter has an incredibly high resistance, which means almost zero current will bother to flow through it. And because no current is flowing through your measurement leads, their resistance doesn't matter anymore. You get a pure, clean reading of the voltage drop across the material itself. It's fantastic.
Now, what's really cool is how the shape of your sample changes things. If you're measuring a big, thick piece of material, what we call a bulk sample, that current you inject spreads out in a perfect little hemisphere. Scientists have the math for that down cold, so they can use a pretty simple formula to get the true resistivity. But what if you're dealing with something super thin, like the materials used to make a computer chip? The physics is exactly the same, but the geometry is totally different. The current can't spread downwards anymore. It's trapped, forced to spread out in a flat, two-dimensional circle. This just means you have to tweak the math a little bit, but the same powerful principle still works perfectly.
And this just shows how incredibly versatile the technique is. For a simple one-dimensional wire, the current has nowhere to spread at all. It just flows straight through. The math becomes even simpler, even more direct. So the four-point method just cleverly adapts to whatever situation you throw at it.
So that's it. Problem solved, right? We've got our perfect measurement. Well, not quite. See, the four-point probe is amazing because it gets rid of some huge sources of error, but it can't get rid of all of them. There's still tiny bits of electrical noise, small fluctuations in temperature, the physical limits of our instruments. All these little things are still there. You can never, ever make a perfect measurement. But what you can do is understand just how imperfect it is. And this is where we have to make a really important mental shift. We've got to stop thinking about errors as if they're just mistakes that need to be fixed. Instead, we need to start talking about uncertainty. And uncertainty isn't about being wrong. It's about being honest about how much we truly know. So let's get formal for a second. The official definition of observational error is the difference between the value you measured and the true value, which of course you can never actually know for sure. But the most important word on this slide is inherent. Error isn't a flaw in your experiment, it's a fundamental part of the act of measuring anything. Now, these errors basically come in two flavors. Think about it like you're shooting at a target. Systematic error is like having the sights on your rifle misaligned. All your shots are going to land off to the side, but they'll all be clustered together. It's a consistent, repeatable bias. Random error, on the other hand, is like having a perfectly sighted rifle, but your hand is just a little unsteady. Your shots are going to be scattered all around the bullseye in a random pattern.
And we have ways to deal with these. For systematic error, if we know our scale is always off by 1 kilogram, we can just subtract it. Easy. For random error, we can take a whole bunch of measurements and average them out to get closer to the center. But what about the errors we don't know about? The things we haven't even thought of? How do we account for all that lingering doubt?
This is where we need a system, a formal language for talking about doubt in a rigorous mathematical way. And the undisputed world experts on this are the metrologists, the scientists of measurement at places like NIST, the National Institute of Standards and Technology in the US. The fundamental building block of this entire language is something called the standard uncertainty. The basic idea is simple. For every single thing that could possibly contribute to the error, we assign it a plus or minus range. It's our way of putting a number on our doubt for each individual factor. And there are two main ways we figure out these numbers. A type A evaluation is purely statistical. You take a bunch of measurements, run the numbers, and calculate the standard deviation. But a type B evaluation is just as scientific and just as important. This is where you use your expert judgment, looking at things like the manufacturer spec sheet for an instrument or a calibration report. It's a way of including all available knowledge, not just the data from your current experiment.
So what scientists do is create something called an uncertainty budget. They literally list out every single conceivable source of uncertainty. But here's the cool part. They don't just add them all up. They combine them using a statistical method called root sum of squares. It's basically a much smarter way of finding the total combined effect of all these different sources of doubt.
And that final number is called the combined standard uncertainty. What it gives you is a range. So if your measurement is, say, 10, and your combined uncertainty is 0.2, what you're really saying is that you are 68% confident that the true value is somewhere between 9.8 and 10.2.
Now, you might be thinking, 68%? That's not very confident. And you'd be right. For a lot of things, it's just not good enough. I mean, if you're calibrating a machine that gives radiation therapy or an altimeter for an airplane, you need to be way, way more sure. You need a wider net, a bigger range, to be more confident you've captured that true value.
So how do we do that? It's actually incredibly simple. We use what's called a coverage factor, usually written as the letter K. And by international agreement, the standard coverage factor used almost everywhere is just the number 2. As this policy from NIST says, the convention is K equals 2. All you do is take that combined uncertainty we calculated and multiply it by 2. That's it. This gives you what's called the expanded uncertainty. And this new, wider range gives you about a 95% level of confidence. And that, right there, is the gold standard for reporting a scientific result.
So, after all that, why does this matter so much? Because this whole framework of uncertainty, it's everything. It's the bright, shining line that separates a random guess from a credible scientific fact. It's how we formally and honestly state our confidence in a result.
In the world of science, a number reported without an uncertainty is basically meaningless. And this isn't just some academic rule. This is what allows a company in Germany to make a part that fits perfectly with a part made in Japan. It's what ensures a dose of medicine from a machine is safe and effective. It's how scientists across the globe can measure the fundamental constants of our universe and know with confidence whether their findings actually agree. So, from now on, when you see a number in a news report, a study, any piece of data at all, don't just accept the number itself. Ask the deeper question, what's its uncertainty? Because in the end, understanding the limits of what we know is the most certain kind of knowledge there is.